making quite a basic introduction on to machine learning and to the astrophysical problem that we're solving, just because I would imagine that we have quite an audience with various levels of expertise, and I don't want to assume that that people know anything that they don't. So this might be obvious to some of you in some aspects at least, but hopefully it will be useful to everybody. So for machine learning, I had this I always start with this clip from a TV series actually called Silicon Valley, which some of you might have seen. And I think it's pretty funny. So let me actually introduce it. So one of the characters has been tasked with writing a classifier that takes a photo of food and labels what food item it is. So he tested on a hot dog, and his algorithm says that it's a hot dog, and then he tests on a slice of pizza, and that's what he gets, right? Because he's just written a binary classifier that tells you whether it's a hot dog or not a hot dog. So the idea, the reason I use this example is that I think it illustrates how machine learning works pretty well, because one of the first tasks you learn when you do a machine learning course, right, is binary classifiers. So imagine that I was trying to build this thing that tells me if this image is hot dog or not a hot dog, right? So I have an image and I want to give it the label hot dog, not hot dog. So basically, in kind of mathematical terms, I have that 128 by 128 by 128 128 by 28 by 3 image, and I'm trying to establish if it's a hot dog or not a hot dog by giving it a label that is. I want to assign it a number that is 0 if it's not, and it's 1 if it is. So the ideal outcome would be this kind of step function where if I give it a photo of a burger of myself, it says it's not a hot dog, and otherwise it says yes. So what I need is a universal function approximator, right? That's what neural networks are, right? The reason they're very appealing is that they can approximate any function, including a function that goes from that very high dimensional space of images to a 0 or 1, depending on whether it is or it isn't a hot dog. So that's the appeal of deep neural networks. And in principle, you could do this with any other function approximator, but neural networks are a very mathematically simple way of expressing any function that you might want to use. And the reason that machine learning has become very popular in the last decade or so is because with the development of differential programming, which means that we can do something called different gradient descent, right? So I just need to set a target that says, here's my universal function approximator, the one I had before, and find a minimum that will be very close to this function. And then gradient descent means that I can very quickly find that minimum. Whereas if I was doing any other kind of traditional minimizing method that doesn't use derivative information, that would be an impossible task. So very difficult things become possible because you're minimizing this million dimensional spaces of neural networks. So those are all of the ingredients that you need, right? And that's my very, very basic introduction to machine learning. All that you have is a universal function approximator, so something that can approximate any function, and a method to convert that any function box into the function that you actually want. And you just have to set up a nice target to make sure that you actually find the right function. Right. So machine learning in astrophysics. So I mean, machine learning, for those of you who work in different sciences, you'll be familiar. Machine learning is kind of become key in all scientific disciplines these days. Just because it's such a useful tool to do things that before maybe took a very long time or were just simply unfeasible. Machine learning is no exception, right? So one of the first things that you can do with machine learning is image classification. So in this slide, for example, I have the example of detecting an exoplanet. So if I'm looking at a star, and I'm looking at the brightness of the star there in that little curve, if I observe periodic drops, that means that something is blocking it at a constant frequency. So that means that there is a planet that is probably orbiting that star. And people used to do this by hand, but with machine learning, you can just feed some kind of noisy data and very quickly find whether there are exoplanets or not in star-like curves. But just like that, you can also, for example, look at a bright object and say if it's a star or a galaxy, what type of galaxy, if it's a supernova. So tasks that we used to do by hand become now very automated and very easy. And that allows us to do next generation astronomical surveys where we have millions of objects and we don't have to classify them by hand. Another one is extrapolation, which any machine learning practitioner will tell you you're not supposed to extrapolate with machine learning, but we kind of try to do it anyway. And the idea here is that if I have, we often have two types of surveys, especially in cosmology, where either you have what's called a spectroscopic survey, which allows you to look at fewer objects, but in a lot of detail, so you can very accurately classify where they are. And then you have what we call photometric surveys, which look at the objects for less time. So the position estimate, let's say, especially the distance estimate, is much less precise. So what you can do is observe a few objects with both of the telescopes, and then try to train something that allows you to extrapolate the distance from one to another. Generating simulations, very important as well. We need this to get an idea of how our models actually look like in reality. And then parameter estimation, I won't go into detail about that because I don't want to bore you. But the point of this slide is that there's many different things you can do with machine learning and astrophysics. But in this work, we're trying to do something that is a bit like one level above, in that we're not trying to use machine learning as a tool to solve a very specific sub-problem, but we're actually trying to use it to do the whole problem. So like we want to feed the data and output the equation, which is basically the job of the scientist, right? So that is the idea of this work. And to do that, we're going to use the solar system as our data set. The reason to do that is the solar system, we have many years of data, and we have dynamic data, right? When you look at further away things, they're moving so slowly that they haven't really changed position very much between the last 30 years and now. But the solar system, we can actually see orbits. So it's very dynamic data and data that we have been looking at for a long time, because people have been looking at the solar system for a long time. So it's a very good data set to do this. So we're going to use 30 years of solar system data to do this work. And we're going to pick 31 bodies, basically the 31 most massive bodies, which will be obviously the sun, the 8 planets, and then some of the moons around the planets as well. Right. So at this point, I like to make a metaphor between what we're doing and the kind of historical discovery of the law of gravity and the first physical law we actually discovered. And that is the kind of Kepler law versus Newton's laws kind of thing. So for those of you who might have forgotten your high school physics or your history of physics or whatever as you learn this stuff, what Kepler did is he looked at astronomical bodies, and he decided to try and make a prediction for where they were going to be. So he came up with these rules that he said, when I look at them for a long time, this is what I see. So he said the orbits are ellipses, and then I can calculate how fast they're moving based on the area of the ellipse. So this is an amazing discovery to just look at these things and derive this. It's truly amazing. But all you can do with this is you can predict where things are going to be next, right? But it's not giving you a mechanism. It's not saying why are the orbits ellipses or why does it cover equal area and equal times. It's just a prediction of what's going to happen. It's kind of like it's found a way of predicting positions, but hasn't understood anything. And this is what we often do with machine learning, right? Like the first part of our work is going to be to fit a machine learning algorithm to solar system data that can make predictions. And that's not difficult. And the reason for that is that that's what machine learning would normally do. We come up with some kind of black box function that can predict what's going to happen, but we don't really understand the black box. We don't really understand the logic. And as scientists, we want to go a little bit further, right? And that's what Newton did when he looked at this, and he said, there's actually this force that predicts what Kepler says. So Kepler was correct, but there's a reason for it, and that means that every two bodies have the same force. And the reason for this is, one is explainability, right? It allows us to go beyond. But another more important one, perhaps, is kind of extrapolation, right? Newton said any two bodies that you pick, any two masses that you pick will do the same thing. So I can apply this to the apple falling from the tree, but I can also apply this to the galaxy moving from the gravitational pull of another galaxy. I mean, he didn't knew there were galaxies, but if he did. So the point is, with when we actually understand what's going on, we can then actually take it to other systems where we haven't seen. Whereas Kepler would have had to like look at the system and try to come up with another prediction. So we're trying to do the Newton thing. We're trying to actually understand and come up with a general equation that describes things. Right. So how do we do this? So we have a two-part algorithm. First, we're going to train a graph network to learn the laws of physics. So like I said, that is the first part of our code, and it's basically what you normally do in machine learning. And you can do it better or worse, and graph networks are very good at it. But that's not, it's essential to the second part. But in and of itself, if we wanted to do this every time, we would have to then retrain the graph neural network every time. But then we're also going to actually extract an equation so that we can actually understand what the neural network has learned. And we can then interpret it. All right, let me talk first about the first part. So graph neural networks. So probably a lot of you are familiar with graph neural networks. Some of you might know more than me about graph neural networks. But it's my understanding that not everybody necessarily knows about them. So I'll talk about them briefly. So the idea of graph neural networks is that just like all the types of neural networks, they do the same thing as any neural network does, but they try to exploit symmetries in the data that are suitable to certain problems. So in the case, for example, of a convolutional neural network, you might be familiar with this example, but the reason people use a convolutional neural network to treat images is that if I have an image with a tree in the middle, and I have an image with a tree, with the same image, but with a tree moved to the corner, if I were to feed like a dense layer to the flattened image, it wouldn't recognize that they are the same. Whereas when I take a convolution, it actually finds the same convolutions, even though the thing is displaced. So the reason people use convolutions, is my point is because it preserves translational symmetry, right? And the reason people use graph neural networks is because they're very good with structured data. So the idea is I'm going to take my data and divide it into nodes. So in this toy graph, I have 3 nodes. Then I'm going to have some edges that connect the nodes. They don't have to, not all nodes have to be connected. In this case, they are. So this would be a fully connected graph, but that doesn't have to be the case. And those I'm going to call edges. And then there can be some global properties as well, but I'm not going to use those in this work. And like I was saying, the reason people use this is because structure systems are very, very good to express with graphs, right? So you can think of any of the ones in this example: molecule, a mass spring system, but also a sentence, right? I really like that example because the sentence is no more than words that are also connected by some kind of causal structure. And using that, you could in principle train any of these things with just a bunch of dense layers on flattened data. But by using the graph, what you get is that you're imposing the symmetries that you know, or the structure that you know, and that makes training much easier. So that is the point of graph neural network, just as it is the point of other neural network architectures. And in this case, obviously, we want to focus on physical systems. And there have been work by one of our collaborators, with Peter Battaglia, on describing physical systems as graphs, where they get a lot of success. So here you're going to see on the top 3 systems true training data, and on the bottom what the model learns with the graph neural network. And when you can see, especially when you look at the middle one, is that it actually hasn't learned exactly the same dynamics, right? So it's not like other types of learning where you learn exactly the same. But I think the interesting thing here is that I think if I were to give you the 2 of them, and I didn't tell you which one was true and which one was the model, you would actually probably not be able to tell me, right? Because they do look pretty much the same. They both look realistic. So the point is that it has learned some kind of pairwise interaction that is realistic, and that's what we're looking for here. And then the second part of our algorithm is extracting the equation. So this part perhaps is less known, but it's obviously crucial to this work. So for that, we're going to use something called symbolic regression, which is something that people have been talking about for a while. So I have here some papers from the 80s from Pat Langley's group, where they started thinking about this kind of stuff, trying to find trends in the data that you can express in equation form. But perhaps the big breakthrough in symbolic regression came with the Eureka algorithm, which tries to express the equations you can see in the bottom right there as some kind of search tree, some kind of usually binary tree. And and you try to find the tree that better serves your data. So it's kind of like a brute force approach. I'm going to explain it a bit more in a second. But it allows you to actually, it gets pretty good performance on at least some reasonably sized, reasonably dimensional problems. Now, the problem with the Eureka algorithm is that, first of all, it's proprietary. And in fact, I believe both of the authors have left academia, so I actually don't know if it's even accessible anymore. And it's also not, it's written in some kind of a GUI that's pretty hard to access. So basically our group, we thought, let's try to write a Python algorithm that does something similar. And that's how we come up with PySAR, where it actually has the same idea, but it actually gets much better performance than the original Eureka. It's written in Julia, so it's very fast, but it has a full Python wrapper so that you don't have to interact with Julia if you don't want to. And it's publicly accessible, so it's on GitHub. This screenshot might be old. I think it's on an older version now, and the author Miles keeps making updates and so on. So feel free to try it out and get in touch with me if you have any questions. But yeah, the idea is the following. So imagine that I have this toy data. So I have some X points and some Y points, and I'm trying to find some kind of Y equals f of X, right? So I might start by saying f of X equals X. And I will get some kind of loss function that I can specify. But imagine that I pick like an MSE, in which case I'll get something that, especially in the middle, and that bump will be quite high. So then you will try something else. So you might try to like rescale the slope of that thing, and then that will give me a slightly better loss because now some of the points are better fit. Then you can try to say like, okay, let's try to put a cosine there, and you'll be like, oh, that's actually much worse. Now things don't really work, and then I can maybe add X plus, and in that case, I get a very good fit. So this is what the algorithm is doing, but it's doing it millions of times, and actually without that much sense in what it's trying. It's mostly just trying a lot of things and trying to find a good one by the virtue of just trying a lot of things. Just because Julia operations are very fast, so actually getting one of these evaluations takes very, very little time. So like I said, gets pretty good performance, and I'll show it in our real case in a few slides. So yeah, we repeat iteratively. And we come up with a set of candidate equations, right? So obviously in this example, I had built the data to follow that equation with some noise, but in reality, you probably won't have as clear a fit. So what PySAR does is it gives you a set of equations that are pretty good fit to the data, and then it's up to you to actually interpret them and think about maybe which ones make more sense or which one you should actually use. Right. So yes, this is actually quite important. So yeah, the algorithm uses an Occam's razor kind of logic, right? So you can always think, again, going back to the same example, that there will be an equation that fits individually every point. With a lot of oscillations and so on. But that, by any reasonable intuition, is not the equation that we're looking for. So it basically penalizes equations by their complexity by a traditional Occam's razor method, which we are actually trying to flesh out in a more theoretical paper at the moment. But the basic idea is that every time I come up with a new equation, the score is the increase in accuracy divided by the increase in complexity. So if I get better accuracy, but the complexity is much bigger, you can see that the score actually will be quite low. Right. This is other work on symbolic regression. I won't talk about it much because of time. It's called AI Feynman, and it's developed by a group in MIT. Also publicly available code, so feel free to check it out. But yeah, I don't have much time to talk about that. All right, so let me talk about our algorithm specifically, right? So we're now solar system data. So first of all, there was this paper by Miles Stramer, the one who did symbolic regression, on doing something similar but with simulations. And he found this was a New York paper. He found that on simulations, things seem to work pretty well. So that encourages to try and push it to real data. So that's what we did. Oops, sorry, that's an old slide that shouldn't be there. So let me quickly summarize the algorithm for you. So our data are the positions of the bodies and their velocities. and that's it, right? And initially, we were considering using the masses also as data, but then we kind of realized that it's a bit unfair to use the mass as data for the obvious reason that the mass is a consequence of the force law that we're trying to learn, right? So if I was learning a different force law, the masses might be different. And besides, we don't observe masses, right? This is maybe something that astronomers are more familiar with, but masses in astronomy are very difficult because we don't see them. So we try to find maybe things orbiting around or light bending around things to guess the mass of things, but it's actually quite difficult. So to be realistic, the masses are not given. We actually try to learn them as part of the algorithm. So our inputs are just the positions of the bodies. So in this, again, toy graph, I have 3 bodies, and those are my positions. That's all the data that I have. Now I convert them into distances. The reason for that is that imposes translational symmetry. And like I mentioned earlier, graphs are really good at exploiting symmetries. And I know that my solar system should be the same if I change my frame of reference so that it moves by a factor, a constant factor, right? So I want to impose translational difference, and I do that by using distances instead of position. Then the model tries to guess a mass for each body, right? So like I was saying, we don't want the masses to be given as data. We want to learn them. So the way we do this is the model tries to add a number to each node, which is going to be hopefully the mass. And that number is a trainable parameter of our model as well. So initially some random numbers, and then we're also trying to gradient descend them into something sensible. And then it guesses a force function. So that function is going to be a function of the distances that connect the things and the masses that it's trying to guess as well. Then it uses Newton's laws of motion. So again, for those of you who are perhaps a bit rusty on your high school physics, we are trying to learn Newton's law of gravity, but we are using Newton's laws of motion. There's a long argument for this that I will not go into much, but I'm happy to discuss this later with you if you're interested. But basically that imposes F equals ma. So that means that I can convert my forces into accelerations for each body. And once I have accelerations, then because I have the velocity also as input data, I can compare my inputs to my outputs. And when I have that, I have a loss function. So I just have to iteratively repeat this and try to minimize that loss function, right? So basically to summarize, I predict the mass, I predict the force function, I use that force function to calculate acceleration, and then I make sure that acceleration actually fits the observed acceleration. So that's all that we're doing. So let me show you some results of what we call this learn simulator, right? So again, this can then simulate solar systems. So this is the data, like I said, that's the data set, the NASA ephemeris system. It's publicly available, so if you're interested in checking it out or playing with the data yourself, have a look. We extract orbits for bodies with above a certain mass cut, which leaves us 31. And we're using 30 years for training and the last 3 for validation. And this is some details about the graph network. I'll pass along the slides later in case people are more interested in the details. It's also in our paper. There'll be some more technical details perhaps. This as well. Okay, this is actually quite important. So like I said, the reason this works pretty well is because of what we call inductive biases, which is, for those of you who are maybe like myself out of physics training, I think inductive bias is basically machine learning for symmetries. So we have all of these symmetries of the system that we're trying to impose in our machine learning architecture so that it knows that these are there, and it doesn't have to learn them as it goes. In principle, it could learn them as it goes, right? With enough training, with a complex enough machine learning architecture, it could learn these. But we know these, right? And these are quite obvious in many cases. So we don't want it to bother learning them, which might take a long time. We'd rather it focuses on the thing that we're actually interested in. And again, this is where graphs are very, very interesting and very helpful in that they are very good to put on symmetries by hand like this. So like I said, we have translational symmetry. So moving our system is not affected. We impose that by using distances. We have rotational symmetry. We impose that by randomly rotating our graph during training. So before actually feeding it to the system, we randomly perform a 3D rotation of the whole system. And by doing that, we're kind of imposing rotational symmetry. Only after doing this paper do we find out about equivariant networks, and like a more elegant way of doing that. So that probably could be future work. Newton's second law, like I said, so that's a way to go from forces to accelerations. Also Newton's third law of motion. So that means that the force between two bodies is equal to the inverse of the force between the bodies going the other way. And then things like reference frame and units and so on, I guess, could be seen also. Inductive biases, as in things that we are telling the system that we know because they make things a bit easier. And you could obviously play the game of trying to get rid of these one at a time and see how well the system does. But we think these are quite reasonable things to tell the system that we know. So I'm now going to show you what we learn when we do this. So again, remember that we're predicting not just the force law, but also masses. And at this point, we're just predicting a black box force law. So we don't actually understand the force law. So what we're doing here is we take the initial positions of 4 of the bodies, and we're going to predict the trajectory over time. Now, remember, when we train, we only train what's going to happen in the next time step, which in our case is 30 minutes. So we just predict what's going to happen in the next 30 minutes. So we haven't trained on rolling over a long time. So as you would expect, things are good on the short scale, but as you roll for a long time, you don't have that stability of circular orbits because you have some kind of black box function. Plus, the masses are probably slightly wrong. So you see that some bodies like Mercury there and Venus actually start to deviate from the truth. The truth, sorry, is the actual planets, and the grids are the learned thing. So you can see that is very good on short time scales, but as we prolong it for a long time, things start to get worse. And this is a more obvious way of seeing it, in that you can see it's the same thing, but just plotted as a paper plot, and that you can see again that at the beginning things are really good, but it's over time that start to deviate. So we need to do better, right? These are, by the way, the predicted masses. Again, some of them are pretty good. This is in log scale. So you can see Jupiter, Saturn, Uranus, Neptune, really, really good. The dots are predictions. We calculate multiple predictions for different random initializations of the masses, just to get an idea of the error and the estimate. And yeah, as you can see, some of them are really good, some of them are really bad. So again, we need to do better. So let's see how we get there, and I'll tell you about this as we followed. So the way we do better is with symbolic regression, as I said. So this will give us more stable orbits because it will actually give us something we can understand. And on top of that, it will give us that nice explainability that we want. So to do this, we select 500 data points from the validation set. Each point has mass 1, mass 2. Sorry about the V notation. Actually, that's the actual paper notation, but in the slides I was using M. But basically, it's mass 1, mass 2, and the distance between two bodies, right? So that's each point is actually a distance containing the two masses and the distance between the bodies. And the output is the force, which we have learned with the graph neural network, right? So we're trying to find an equation that fits the force we're learning with the graph network. And we're going to play this game. In this case, Y is again going to be what we learn with the graph network. X is going to be, like I said, masses and distances. And this is what we get. So like I said in the beginning, we get a list of candidate equations. And you can see them there on the left. The light blue one you will recognize is actually Newton's gravitational law, the one that we're hoping to find. But there are other ones that we should consider, right, on the left. So what we do is we play this game of rolling out trajectories over a long time for each one of these equations and seeing the error between the true and the predicted. And you can see that on the plot on the right here. First of all, you can see that Newtonian gravity, the true force law with the true masses, is actually not perfect. It doesn't have a zero error. The reason for that will be things like relativity, but also missing bodies, screening effects, and so on. Basically, Newton's law doesn't actually fully capture the dynamics of the solar system. But obviously, the error is very low when you do that. And you can see that our light blue, it's very, very similar. And the reason it's not the same is because even though it's the same equation, it doesn't have the same masses, right? Because the masses are the ones that we learn, and we saw they're not quite right. So to make things better, what we do is we try to refit the masses. So we go back here, and what we do now is we scratch the force guess then we put the force that we have learned with the equation, which is Newton's law. And now we're just trying to learn the masses properly. And what you get is this is the masses we had before. These are the ones we get now. And you see that that now basically all of the bodies we get the dots still have multiple iterations. I believe it's 10, but you cannot see them because they're almost always spot on. You might notice that there are 3 bodies that are not very good, the mass estimates. I'll get back to that in a second. But first, let me show you again the same I showed you before, but now with the final equation plus learn masses thing. And you can see that now actually our prediction fits the truth really well, even over a long period of time, which again is not what we've trained for. But by simplifying from the black box to the actual equation, we actually get much more stable orbits, which makes sense, right? Because we expect physical laws to be, hopefully to an extent, something we can express with an equation like that. This is the similar plot from before. You can focus on the top and the bottom there. You can see how at the bottom, in the final thing, we actually get very stable orbits. Now the masses, like I said, some of them are not perfect. You can focus there on Hyperion, Phoebe. So why is that, right? Why are we not getting very good masses there? Now that was a bit of a puzzle for us for a while. We were trying to understand that. But then when we came up with the answer, it's actually quite elegant and quite reassuring that we're doing something right. And the answer will it will make more sense to those of you with maybe a physics background. But I'll try to make it obvious for everybody. So there's this thing called the principle of equivalence. So this is one of the main things that Einstein kind of came up with, and he came up with all of these thought experiments, right? And his idea was, if I am free falling in an elevator, that is exactly indistinguishable from what would happen if I was floating in space. The point is that I'm just following my trajectory in space-time, and those two things are then indistinguishable. But one way of re-expressing that is your movement does not depend on your own mass, right? So this is a consequence of the equivalence principle, and it kind of comes back to the whole to the idea we were talking about before. The point is that if I become twice as massive, I will move just as fast, because what makes me move is the gravity created by some other body that I'm following, not my own. So in other words, back to our problem, we can only measure masses by how much they influence other bodies, right? The mass is never going to influence the body's own motion, so we can only measure them by their influence on other bodies. Now, going back to these, we were quite suspicious when we realized that probably the ones we were not actually learning very well were actually the ones that don't influence the system that much. And that's what was happening. So what we did was try to come up with a way of calculating how much each body influences the rest of the bodies in the system. And when you plot that, you find that the ones that influence the system less, so that would be the x-axis in this plot, are the ones that also get the biggest error in the mass. So those 3 that I was showing you in particular are the ones that very, very clearly do not influence the rest of the bodies. I can give you more details about how this is calculated if you want to follow up later, or it's also in the paper, of course. But the point is, the ones that we're not getting masses for are the ones that are actually not influencing anything. So it actually would be concerning if we were getting their masses right, because they're not influencing anything. So their masses are kind of irrelevant to the system. And so go back to this plot, we know the mass is not really high, because then they would actually start influencing things. But all that we can get is like a mass, like a top of how massive they can be. But below that, nothing really changes, because they're just not influencing anything. So this is actually quite reassuring that we're actually doing the right thing. And now, if we were to add more bodies, if we lower our mass cut and added more bodies that maybe are influenced by these, then we'll probably get the masses of these correctly. But the smaller bodies we couldn't measure. So that's the point. We only measure gravitational influence by influence on other things. So short summary, and I think I'm about my time deadline, so that kind of works. We're using graph neural networks and symbolic regression on 30 years of solar system data. And we managed to get the correct equation for Newton's law and the masses of the planets and moons from the data directly. This only works because of all of these inductive biases, like I said, all of the symmetries that we know. And hopefully this shows the potential of AI to help us automate scientific discovery and maybe try to solve some of the mysteries of physics and of science that have kind of remained till today. And I'll leave you with that. Thank you.